Great. So welcome back to CS 194, lecture 2. And we're going to talk today a little bit about more about memory hierarchies, a little bit of review of 61C, and then talk about optimizing matrix multiply, which I realize you also did in 61C, but I think this will be a little bit different from what I can tell. I wanted to go back and do course logistics. So I apologize for last week's lecture. My note to self, don't fiddle with your display settings the day before your first lecture. So I figured out what the problem was, but it wasn't until after lecture. So I actually re-recorded the whole lecture. So if you want to go back and look at it, it hopefully is a little bit easier to see the slides and things like that, but also recorded than the beginning that wasn't on the other recording. But I wanted to also go over the course logistics a little bit that kind of ran out of time for last time. There is a course overview document on the website, so be sure you look at that. It has a bunch of information about when the homeworks are due, when the quizzes will be, all of those kinds of things, and a lot of other stuff about the class and how it's set up. And I'll say just a little bit more about that. So as I think hopefully everybody knows by now, instead of having 3 hours of lecture a week, we're going to have 2 hours of lecture and 1 hour of lab, and that will be run by Ben Brock. In addition to that, you should be assigned a homework group. So you have a group of people that you can talk to if you run into problems in your homeworks, and you'll be working with them in the lab as well. To get access to Piazza, you should all be reading Piazza. Lots of great conversations about homework 1 there already. The password is parallel. I did want to say a little bit more about these homework groups and how this fits together with turning in your own work. So the work in this class, and the grade breakdown and everything is in the overview. It is not the grade. The course was not going to be graded on a curve. It's an absolute grading scale, so you can look at the grading scale there. So there is. So you're not competing against one another. But that said, we do expect you to do your own work. What that means is that you're welcome to talk with people, either on Piazza or in the or in your homework groups or with other people in the class. I encourage you to talk to your homework groups kind of first, because it helps other people in that group. If you're somebody who maybe is a little bit further ahead, it will help other people group, and we want everybody to have that kind of experience. But that doesn't mean that you turn in their work. You turn in your own work. You talk to them about it. You should, the easiest rule is never have anybody else's code. You shouldn't really be showing them your code. If there's a small thing you need to help them debug, like an error message that you're looking at, I understand that, but you shouldn't have their code in your possession, and you should never give your code to anybody else. That includes, by the way, after the semester is over. I don't know the next time that we'll be teaching this course, but some parts of it are shared with other courses, and you really are not allowed to put your homework solutions in public. So make sure your GitHub repos and things like that, well, presumably in the class, that's all private, but that you don't put it out someplace in the public. So, and hopefully that's all clear to people. I think it's very similar to the same kind of standards you had for sharing and cheating and things like that in CS61B. I modeled the overview after the 61B overview. That's because I used to teach that course, and I'm very familiar with that and how it runs and things like that. But the difference is we do have these homework groups, but that doesn't really change the fact that you still need to turn in your own work. There's my email address and Ben's email address. I think you've gotten to know one or both of us through Piazza and email by now, but if you have questions that you don't want to ask in Piazza, please email both of us, and also include CS 194 in the subject line. It's much less likely I will lose it in my inbox. Any questions about course logistics before I go on? You can type them in chat, or you can raise your hand. Let me see if I can see all of your hands. Okay, great. All right, so this was also in the email that you got this summer, but just to be clear, there's really 4 units in the class. There's a quiz per unit, and there's a topic per unit. We are in the middle of the serial performance programming unit, and we're going to be looking at performance programming and also really the hardware and software interface today. And the rest of the semester, we'll be looking at more at parallelism, at parallel algorithms, at different patterns of parallelism that come up in applications. I'll say a little bit more about those patterns though today. So I wanted to also say a little bit about what is Cori, and I think most of you probably got this answered through reading things on the internet, asking questions on Piazza or so on. But just to be clear, so Cori is a supercomputer that is made out of many racks of computers and of processors. It actually has 4 rows of cabinets. This picture isn't exactly written in the right shape, but anyway, it gives you a basic idea. It's a whole bunch of processor and memory nodes. So those are the nodes in it, and it has 2 different kinds of processors. It's got Haswell processors and it has Knights Landing or KNL processors, and that's just some details about how how things are put together. So and there's a file system connected to it. Your home directories are there. Your home directories are backed up. There's a big scratch file system. Probably you won't be using very much storage today, and there's another storage system as well, but for the most part your assignments will not require very much storage. There's some other nodes in there that are called the burst buffer nodes that have SSD. You're coming into something called the login nodes, these green nodes down here, which are also Haswell nodes, and so we'll say a little bit more about those in a minute. Okay, so when you are launching parallel jobs, you're going to be using something called Slurm, and you can use that already with your serial jobs. And so one rule for the class is, as much as possible, you should be using the KNL or Knights Landing nodes, not the Haswell nodes. Now you have to log into the Haswell nodes because that's what the front end nodes are. And once you're on the front end, you can do a SBatch, which is to run a batch job that will happen in background, or you can SAlloc, which kind of allows you to log into some of the compute nodes. And so this just gives you an idea of sort of the picture of how things are put together. And from the login nodes, here's an example. If you wanted to, if you want to run a batch script, you can put together a file that has the script in it. It is a bash shell. That's what this file is. And this was my batch script for running homework 1 assignments. I got really tired of typing in numbers and stuff like that. And so here's a little script that ran all the different sizes that I wanted to run. And I'm going to run it on the KNL nodes in something called the debug queue, only on a single node for a couple of minutes. And so I then do an SBatch on this file, and it goes and launches the job on a node. I can then do other things. I like to multitask a lot, and so all the of course, even if you're sitting there at the prompt. But anyway, I can now go do some other things and then check the queue to see if my job is done with SQS. And typically it came back for a small job like this. It comes back in just a couple of minutes. And then the output goes into a file called Slurm with some file name that is made up based on the job ID and a .out. So the other thing that there were lots of questions about is how to set things up so that you're not SCPing or whatever your files back and forth, and also how to run GitHub and things like that. Ben is here and he can tell you many other ways of doing this and much more sophisticated ways, and he's got lots of scripts and stuff that do this, but just kind of a simple thing that I do, because I like to keep things simple, is I start a window on Cori. This is going to be the green window, and I have another window on my laptop, and then I have my favorite editor, which in my case is Emacs, but you can choose whatever editor you happen to have installed locally on your laptop, and that can also see the files that are on Cori. So how do we set this up? Well, the first thing I do is once a day, I run something called SSH proxy. If you don't have that installed, you should copy it from NERSC. That will allow you to type in your password and your one-time password key just once a day instead of once every time you log in. And then the next thing I do is I mount my Cori file system. I do that with SSHFS. There are other ways of doing it. And this, you have to give your login name. It tells you, and this is the subdirectory name. So in the blue window here, you can see that I've done that. I've done SSH proxy, and then I've done SSH FS. So first of all, I already had a subdirectory called Cori. There was nothing in it. So when I first do an LS on Cori, it's empty. Then I do an SSH FS. And it mounts the directory, my home directory from Cori, into this subdirectory called Cori. That's all the stuff I have in my home directory. And then from there, I can open any of the files. So for example, I can edit my file over here in my editor. Oops, sorry. there it is, locally edit it, my editor. And when I save back on Cori. Now I do have to be sure that I compile and run jobs on Cori because the compiler is different and the hardware is different. It has to compile for that hardware. And by the way, I can also run Git locally on my laptop if I want to. So let me just make sure there are no immediate questions. I don't see any in the chat. Okay. So on to the sort of main topic of the course and of today's lecture. And I showed this graph last time. You'll probably see it again many times, looking at Moore's law here, which was still going strong in terms of the number of transistors per chip, and transistor density was growing, and single thread performance though leveled off and the frequency leveled off. So I was the director of NERSC, which is where we have Cori, in 2008. And here we are sitting here in 2008. It was pretty clear already that performance had leveled off. So what were we going to do? We wanted to have one of the fastest computers in the world. We have 7,000 scientists. They use this for everything from climate modeling to developing solar panel materials and all kinds of other important applications. So we want a fast computer. Well, what we decided to do was go with this kind of small cores, and my successor, Sudeep Dosanjh, who's the current NERSC director, continued in that vein, and that's what led to the Cori system. And so why did we do that? We did that because, although you don't see it on this particular graph, as the clock speed increases, so when these blue squares here, when the clock speed was increasing, we are also getting more heat density. And so in order to get to keep the chips from overheating, we actually just made the clock speeds even somewhat slower in some cases. We'd kind of over-engineered these processors just a bit. So we slowed them down, and then we used those extra transistors that we didn't need for making a much more complex, larger processor and put them into more cores. And so that's what you'll see on the Cori system. So there's, as I mentioned, two nodes on Haswell, on Cori. There's the Haswell nodes, and Haswell has 16 cores on each chip. We'll call them sockets because each node is a shared memory node. It's got one set of memory. Oops, now I'm in front of this, so it's got 128 gigabytes of memory on each one of the nodes. And it's got two sockets, so two of these processor chips, each of which has 16 cores, and those cores run at 2.3 gigahertz. And it has a 256 byte wide vector unit. And for each one of the floating point operations, if you're looking at what's the fastest thing it can do a fused multiply add. So it can do a multiply and an add in a single cycle. And it can do it on 4 of these 64-bit elements and one of these 256-bit wide vectors. And so there's the computation of the 3.6 gigaflops per core, and then you get 1.2 teraflops per node from the 16 times 2, so the 32 cores that you have on a node. Okay, so that's what Haswell looks like. As I said, we won't be using it very often, although there are compute nodes on Cori in addition to the login nodes that are Haswell nodes. But we're primarily going to focus on Knights Landing, which actually has 64 cores. So this is now, and it's got a slower clock rate than Haswell. Each one of those cores has less area, so we can get a much larger number of cores, hence the 68, but it also uses less power per core, so it keeps us from overheating this chip, even though it's got so many cores on it. And here's a little bit more detail of what Knights Landing looks like. It's got the Knights Landing socket is a single socket in this case, so it's just a single Knights Landing chip with 68 cores. It runs at only 1.4 gigahertz, so you'll find that the running time on KNL is going to be slower than Haswell on, say, the login nodes. By the way, you shouldn't run much on the login nodes. We didn't worry about it too much for homework 1, but for homework 2 and beyond, we really want you to use the Knights Landing nodes. Each core has 4 hardware threads. And those threads don't matter too much for the peak performance as we're counting it, but it does allow you the processor to keep multiple things going, and going back to Little's law, it can have more outstanding things happening. So you can have 4 threads. So the question was there was a question about what the sockets are used for. The socket is just another name to think of it as it's the thing you plug the chip into. So just think of it as the chip. It's really, as we're using it here, it's really synonymous with the chip. And so the socket is used for everything here. We sometimes use socket because sometimes the socket on the board can be compatible with other chips. And one of the things we've done on some of the other NERSC computers is popped out the chips and put in a chip with more cores. We did that once on a system called Franklin, where it came with dual core chips, and then we popped those out and put in quad core chips about a year later. So, so then here's the calculation of the peak performance on this email. Sorry, I'm getting an email interrupt here on this, on each one of these nice landing chips. Okay. So, all right, so how fast does this actually go? Well, we're gonna really be interested in a couple of different things. One is how fast is the processor itself? That's the kind of speeds and feeds we saw in the last slide. What is the flop rate? And we'll talk in a lot more detail about those vector units and things like that as we move into home a little bit later in the next week or so. But right now, I just want to really focus on the memory system, because the first thing we're going to focus on is how to optimize for the caches in the memory system, and maybe for the registers as well. So here's a little benchmark that's comes from the CacheBench benchmark suite, which you can download. It's open source, and you can download it and run it on your laptop if you want to. And this is a little bit of pseudocode for what the benchmark looks like. It's just running through an array of a given size. And it is accessing, reading every element of that array. And as you learned in homework 1, hopefully if you've finished it, you know that you need to print out the value at the end. So it doesn't show the print statement here, but it needs to print out that value. Otherwise, the compiler might get really smart and throw away the entire loop. So you would write out the value of R at the end of this. But outside of this loop, and we're going to run this for multiple iterations. Why are we doing that? We're doing that because our timer granularity may be too coarse, that, and we want to really measure just the cost of each one of those memory operations. And so what we are doing is running a large number of iterations so that we can then average over them, and in order to figure out what the time is for each iteration, and then the time for each one of those operations is. So from that, we can get a bandwidth number, as well as a trip count, or the cost of each one of those iterations. But we're also going to vary the length of the array. So this memory array, in this pseudocode here, I'm going to try a whole bunch of different vector lengths. And so in the green pictures over here, I've got these different vector lengths. If I've got a small vector, it's going to fit inside of my cache. And so when I do it over and over again, I will have warmed up the cache the first time through. And then after that, I'll keep accessing that same array, and it's sitting inside of the cache. And so what I'll be measuring for these small arrays is the memory bandwidth. What I'll be measuring for the larger arrays, is the cache bandwidth. For the larger arrays, then we'll see that the performance will go down, and the time will go up, and the bandwidth will go down. And that's because once the array does not fit in cache, I will be missing in the cache sometimes on every one of the elements. Okay, so this was some numbers taken, running that benchmark from one of my students, Julia Goody, who recently ran this on the Cori system for all of you. Actually, she was doing it for a paper, but anyway. And so this shows you what the kind of cache output looks like. And I should mention, by the way, there's a write version of that benchmark that's writing into the array, and so on. And there's also and there's another one that's doing an update. So what do we see from this? Well, this shows both the Haswell and the KNL. You can see that the memory bandwidth on KNL is quite a bit lower than on Haswell. That's, I think, in part because we're only using one thread in this particular benchmark, and we'll need to use multiple threads in order to saturate, to sort of be able to saturate the memory system. But you can see from this how you do get better performance when your vector size is sitting here in the cache, and once you fall out of the L1 cache, your performance will drop, and when you fall out of the L2 cache or others, it drops even further. And from this, you can get a measurement of what the memory bandwidth is, and you can also get this estimate of the cache sizes, although it's not exactly lined up with the hardware cache sizes here. And that can have to do with some details of the cache architecture. But And you'll notice that the Corey-Haswell system has a pretty uneven bandwidth number here for the when the data is sitting in cache, and that may also have to do with some details of the cache structure, or something, that it's not always running at its bandwidth. It also takes kind of a while. There's some of the loop overhead and things like that that may be interfering. All right, so if this is a class on parallel programming, why are we spending almost 3 weeks talking about serial performance? And we'll talk more about matrix multiply today, but this is just to give you one example of how much improvement you can get in serial performance. This is looking at a naive version of matrix multiply. This is runtime, so down is good here, and whereas the previous slide was bandwidth. And so the and there's about a factor of 130 between these two serial versions of the code. Now the parallel versions of the code, which are the purple ones, and then the GPU optimized code, which is the blue one, are even faster. But even getting from this serial code up to the optimized serial code, there are 2 orders of magnitude in performance. Now matrix multiply is sort of an extreme in terms of the amount of speed up that you get from some of these kinds of optimizations. That's also a reason that we tend to use it in this course, is because it's something that really highlights the value of these memory optimizations. They're sometimes harder to see in other things, although it'll often be an order of magnitude rather than 2 orders of magnitude for a lot of other problems. Okay, so there's our cartoon that I showed last time of our memory hierarchy. I don't think I'll spend more time on it now, and hopefully you're familiar with this from 61C. I'm now going to talk a little bit about applications and how we're going to look at applications in this course. I think even early on when Ben and I started talking about developing this course, we were thinking about having some larger project in which you would work on one of these large application problems. I think just given the nature of the course and to give you experience with a larger range of algorithms and things like that, and spend more of your time hopefully doing interesting work rather than kind of dealing with monstrous pieces of code, we decided to have you work on some of the kernels that I'll talk about in a minute. So, where are the places that people need very high performance? Well, we certainly use it a lot in simulation problems and scientific and engineering simulations. This little picture is a picture of a very high performance simulation that I think ran on almost all of Cori of the Hayward Fault, an earthquake simulation of the Hayward Fault. And we simulate everything from atoms to atomic scale characteristics to the universe. Data problems, so we will look at some examples of algorithms that come up in things like genomics and images, and we'll also look at machine learning. So matrix multiply, which we'll talk about later today, is especially important in deep learning in particular. So let's see, in about 2006, we wrote this paper. We spent a few years working on it beforehand, talking about how to think about a lot of different applications and how to address the change, which at the time was just the beginning of the multi-core era. So we were just starting to see multiple processors on a chip. Before that, most people worrying about parallel computing were working at supercomputing centers like NERSC, and suddenly I started getting phone calls from companies like Intel and IBM saying, hey, we think we need to learn a lot more about parallel programming, and asking lots of questions about that. And they funded, Intel and Microsoft actually funded a project called Parlab at Berkeley, and this was kind of the canonical picture. What we did was looked at some real applications. So a health application, looking at blood flow in the arteries and how to make quick decisions based on these simulations, an image analysis problem, a speech analysis problem, music, and which you might not think is a high performance computing problem, but actually turns into one. And then something that is looking at how you actually implement a browser and use parallelism inside of the browser. So there's a whole class of applications here on the left, but what we developed was this list of what are called the 13 motifs or patterns, if you will, of that come up in terms of parallelism, and dense matrix operations are here in the middle. You can see there's a lot of red means that this is important to this application or to this class of applications on the left. Blue means it's not important. Green and yellow are sort of somewhere in between. So it's a dense linear algebra, dense matrix operations are important for a lot of different problems. Now, we've looked at a number of different ways of trying to divide these things up, and other groups have as well. The original list actually that motivated those 13 motifs were a list from Phil Colella that he called the Seven Dwarfs, after Snow White and the Seven Dwarfs. And this was his list of things that come up in scientific simulation problems. So you see dense linear algebra there as well. Then a National Academies group got together, including Mike Jordan and others. I think Michael Mahoney was on that, and put together a report on the 7 giants of big data. And it has some of the same things, and it's got linear algebra, both dense and sparse. They wanted 7, so they combined them into a single one. And most recently, I wrote a paper looking at some of the patterns that come up in genomic analysis. And what we found is pretty close to what the National Academies group had, except I think that hashing and sorting, which are also things that we'll look at in this class, hopefully we'll get to do both of them, are also very important. So we'll look at some of these computational problems, and I'll try to give you an idea of how they fit into the larger applications. So why matrix multiplication? Well, it comes up in a lot of linear algebra algorithms. It's used in the top 500. So people have spent a lot of time making it run fast. So the top 500 is the list that I mentioned last time, where we rank all the fastest 500 machines in the world. And so people spend a lot of time making that's the dense LU factorization, but most of the time is spent in dense matrix multiplications. It's one of the motifs, as I mentioned. It comes up in a lot of different applications. It's closely related to other algorithms that we'll see. So for example, a number of graph algorithms can be formulated as a matrix algorithm, either dense or sparse matrix algorithm. And I'll say more about what a sparse matrix looks like in a future lecture. Perhaps most important, right today, it dominates the training time in deep learning algorithms and convolutional neural nets. And I'll say more about that in a minute. The optimization ideas we use here will also be used in other problems. And it also, as I mentioned earlier, kind of is the best case. So we'll see sometimes a couple of orders of magnitude of performance improvement. And it's probably one of the most well-studied algorithms. So in 2018, these 3 individuals won the Turing Award, which is the highest level award for computer science. And this was for their work on deep learning. And there's the Turing Award bowl that they got. And in Geoff Hinton's acceptance speech as part of the Turing Award lecture, they gave a combined speech, and I was there. He said that a lot of the credit for the deep learning work actually goes to the people who collected big data sets, like Fei-Fei Li, who's at Stanford, and people who made the computers go fast, like David Patterson and others. David, by the way, Dave Patterson was also sitting in the audience, so maybe that's why he picked Dave out, but obviously many people have made processors go fast, and I think many people in the machine learning community will say that what really made these algorithms successful was not the algorithms themselves, it was the access to large data sets and the speed of the computers. And the things that we're doing today in terms of training neural nets, and I showed you one example of how expensive those are last time. And what he maybe didn't mention is also the people that figured out how to make these, how to map these algorithms onto it, including their own group. But mapping these algorithms onto hardware is very important for getting good performance. So this is a graph that I like, was on matrix multiply. It was from a former student at Berkeley who's now on the faculty at Cornell, who took the graduate version of this course, CS267, many years ago, but now teaches a course in parallel computing and scientific computing. So what does this show? Well, this is a matrix dimension, and this is the speed of matrix multiply. So this is in megaflops, so up is good. Here is the naive algorithm, and we'll look at that one in a minute. I think it's, by the way, pretty close to what you did in 61C. And then we look at he looked at a blocked algorithm, which is this green curve, which is much better performance. You can see where even for the naive algorithm, the matrix fits in the cache. So it's running the matrix multiply over and over again. So that's why you're getting very good performance when the matrix, I think, when the matrix fits in cache. But even so, you're reusing all the elements of the cache of the matrix, and so that's why you're getting good performance. But it really falls off when the matrices don't fit in cache. The blocked algorithm is better, but you'll see really jagged performance. You may see something like this on your homework assignment. And then he built his own optimized version, which was much more consistent performance and a little bit better than the others, even in the best cases. However, the vendor also optimized matrix multiply. So there are all three of the same curves down here, and this is the performance that the vendor got out of the same hardware. So as you can imagine, a lot of time goes into optimizing some of these kernels, especially things that are now so important to machine learning. And so this just gives you another idea of the importance of these kinds of serial performance optimizations. Okay, so we're going to look at matrix multiply, and before we do that, I want to just mention to think about how we're going to lay out the matrices in memory. There are two ways of laying them out. So we've got a two-dimensional object we have to lay out in one-dimensional memory. Memory is just one big flat line, and so they can be either row major or column major. I think that you also talked about this in 267, so I won't belabor it except to say that whatever you do, whether it's column major or row major, if you're accessing things in the opposite direction, not only will your accesses be jumping through different cache lines, but if your matrix size is not a multiple of the cache line size, which is the picture that we have here on the right, then, so this is, say, accessing, if it's a column major layout, these red things are all of the cache lines I need in order to get this, this element in, this set of elements that are going across the rows in green. And so those red lines might be a little bit better if they were all lined up with each other, because then as you went kind of around to the next row, you would be continuing to hit in the cache as you go through those. But as it's laid out right here, because of the shift, because the matrix dimension is not divisible by the cache line size, you're getting something that looks like this. So let's see. And we're going to use a simple model of memory to think about how fast things go. So now we're getting a little bit of algorithmic analysis here. So we're going to just assume that there's two levels of the memory hierarchy: fast memory and slow memory. And of course, we know from the picture and from your experience in 61C, there's multiple levels of memory hierarchy. There's registers, L1 cache, L2 cache, sometimes L3 cache or more. There may be other layers, victim caches, and so on. But let's see, but this is looking at the just two levels of the memory hierarchy, so a slow memory and a fast memory. So M is going to be the number that, or the formula that we're going to try to calculate for a number of different problems. That's the amount of memory, and the number of words in this case. We could do it in bytes, but the number of words that we move from the slow memory into the fast memory or back again, either reading them from slow to fast or writing them from fast to slow. T sub M is the time it takes to do one of those memory operations. So this is going to be, in the best case, the inverse bandwidth. We're going to just assume it's constant right now, although we know from the discussion last time and hopefully from your own experience that latency is going to be much longer than the average time per element in terms of the peak bandwidth of the memory system. But we'll just assume this is a constant here. The number of arithmetic operations you need to perform, and then the time to perform each arithmetic operation, which is T sub F. And that is going to be, of course, much less than the time to move memory, even in the bandwidth sense. So the computational intensity, which I'll sometimes call Q, and I'm calling computational intensity here, is the average number of flops per slow memory access. So this computational intensity is something that will come up a lot in other algorithms. If we have good computational intensity, that means we can run a lot of things in the cache in the fast memory. If we have very low computational intensity, we're basically going to be running at memory bandwidth speeds. So the minimal possible time, if we didn't have to worry about memory at all, would be the total number of floating point operations F times the time per floating point operation. By the way, we can do the same analysis for non-floating point computations, for integer computations, or things that are doing logical operations. I'll just use floating point here because it's flops because we're doing matrix multiply. So the actual time, though, is going to have that term in it for the floating point operations, but it's also going to have a term which is, so there's the 1 times that plus the amount of time it takes, the number of time it takes per memory operation over the flops. That is the machine balance. So the machine balance is, what's the ratio of memory speed to flop speed, and then the computational, 1 divided by the computational intensity. So a larger computational intensity means that this term will get close to 0, and then we'll get close to the that best possible running time. Okay, so there's a couple of questions in the chat, and I just want to go back for a minute to, I think it's this graph. This is megaflops per second. Maybe it was even before that. All right, well, I think I won't. Let me see if there's a hand up. Okay, so these graphs are both in megaflops per second, and we'll have to look later and see what the other ones were. I thought it was a recent question. All right, whoops, let's see, I'm going ahead too far. Okay, so there's our simple performance model. So for a warm-up exercise, we're going to look at matrix vector multiplication. And I believe you also did this in 61C. So hopefully this is a review. So here we've got our 2 nested loops for I equals 1 to n, for j equals 1 to n. By the way, I'm using 1-based indexing just so to avoid the -1s or the less than's and stuff like that here. But you'll be working in 0-based index arrays. So if I'm going to do a matrix vector multiply, I'm going to multiply a row of this matrix times this vector. So doing a dot product on these 2 blue lines and getting a single element that's going to be added to the result array. So there's our matrix vector multiply. So how much data movement do we have for this thing? Well, we have to read the vector x into the fast memory, and we have to read the vector y, which is the result, into fast memory, because we're going to write on top of it. We could avoid this read maybe if we were going to just do a overwrite of y, but we're going to do an update of y the way the code is written. And in any case, we're going to have to write y back at the end. So we've got both the read and the write of y. We've got the one read of x, and then we need to read a row of a into the fast memory. So that is happening inside of here, and we're writing this as if we're actually controlling the movement of these pieces of X, Y, and A from the slow to the fast memory, when in fact the cache is typically doing this for us. And we're hoping that it's moving in sort of a piece of it, at least a piece of it at a time, and we'll leave as much of it there as it can. So what is our memory cost here? So remember, M is the number of slow memory operations or references to and from memory. So there's 3n of those. For these 3, the x, the y, and the y at the end, and then the n squared of them for all the elements of A. And the total number of arithmetic operations is 2n squared. And so this has a very low computational intensity of about 2. So it's just got a computational intensity of about the 2n squared divided by the n squared, and ignoring the 3n here. And so that says that matrix vector multiplication is going to be limited by the slow memory speed. Okay, so we made some simplifying assumptions here, actually several of them, although it's still a useful analysis. So the first assumption we made is that there's a constant peak computational rate. So I just called that T sub f. In fact, what we'll worry about later in the week, at least within the next week and a half, is exactly how do you get good performance out of the processor itself. We also assumed that the fast memory was large enough to hold 3 vectors. It didn't have to hold the whole matrix A, but it did have to hold the 3 vectors. And by the way, that the organization of, say, that cache was laid out in such a way that they're not all interfering with them. If you had a direct mapped cache without any associativity, they could all be living in the same part of the cache, and that would cause a lot of problems for the performance and for the way we've done the analysis. And we also assumed that the cost of a fast memory access is 0, which might be a reasonable assumption for registers, but probably not even for an L1 cache where it's going to be a few cycles. And the memory latency, we assumed, is a constant number. Actually, really it was, the way I'm thinking about it here is really the inverse bandwidth, at least, is the best. But in any case, we've kind of conflated those into a single number between the latency and the inverse bandwidth. We could further simplify this by ignoring the memory operations to the vectors x and y because they're small, they're only order n as opposed to the n squared things. And that's not a bad way to come up with an even more simpler approximation, which is the time to run this algorithm is basically going to be the time to read the matrix, because it's almost certain that the time to read an element of the matrix is going to cost more than those 2 floating point operations to operate on it. And that says that the bandwidth is going to dominate this computation. And there's not too much we can do about this, right? You have to read the matrix in order to multiply by it. So it's not even something we can optimize very much. Okay, so now let's look at a more interesting case, which is matrix multiply. And here we've got our 3 nested loops now, and a little diagram of what we're multiplying. And the way this is written, it still is written as a dot product here. So we're taking a dot product of this vector of A and this vector of B, column vector of B, multiplying them together and computing an element that updates one element of C, which is Cij. So the algorithm has 2 n cubed flops, or order n cubed flops, and it operates on 3 n squared words of memory, the 3 matrices. So the best computational intensity you could possibly have, like just assuming you have unbounded caches, is going to be 2 n cubed divided by 3n squared. And that's going to be order n, which is great, right? So any computational intensity that is non-constant. So a lot of times we'll write these computational intensities not as a big O thing, but as a constant, because we really care if the computational intensity is 16 versus 1, or 128 versus 2, or whatever. That'll make a big difference in how fast or how efficiently it'll use the hardware, what percentage of peak it's going to get out of the hardware arithmetic units. But in this case, because it's actually order n operations we're going to be doing, if we can figure out how to organize this the right way, we could potentially get something like order n reuse, and which means order n computational intensity. So, well, let's look at our naive matrix multiply and figure out how much memory memory traffic it's going to have. So the first thing we'll do is, and once again, we're just going to assume we can load exactly what we want to into our fast memory. So we'll read a row of A in, and then we will just read one element of C in, and then we'll read in a column of B, and then we'll do the multiply and the add on all of these, so the dot product in there, and then we'll write back just that one element of C. Now when we go on to the next one, you'll notice, because of the way this is written, that we don't need to read another row of A, we just need to read another column of B. And so what is the memory cost going to look like? Well, it's going to still be it's going to be n cubed to read the columns of B, because each column of B is going to have to be read n times, and there's n squared elements of B. So the n times that we read each one of those columns means that we're reading each element n times, and so it's n cubed reads of the elements of B. And in addition, we have to read each row of A. We're only going to read it once, so it's only n squared. And we have the 2 reads, the read and the write, sorry, of C, which is another 2n squared. And so that's going to be our total memory traffic is in this particular algorithm is n cubed plus 3n squared. Now we're still, by the way, assuming that we can save these vectors in the fast memory cache as we did with matrix vector multiply, and we're assuming that the whole matrix A does not fit into the fast memory. And so the computational intensity here is 2n cubed over n cubed. So it's about 2. So it really isn't any better than matrix vector multiply. Not too surprising, because we're actually built this on top of matrix vector multiply that had that computational intensity of 2. So let's block this algorithm now, or tile it. Those are 2 terms that people use to talk about the same thing. Blocked gets used in a number of different ways unrelated to this in computer science. So we try to use the word tiled, but we often use blocked instead. So let's think of the matrices now as being themselves full of matrices rather than having them full of just individual elements. So think of Cij, this little blue block is not a single floating point number, but it might be something like a 4x4 block or a 256 by 256 block. And in general, these blocks don't have to be square, but we'll just assume they are for simplicity of this presentation right now, and we're just going to do some analysis on them, so it won't matter. So now we can think about we've got the same code here, but there's a big difference, which is this multiply right here in the blue line. And this add right here, this is a matrix add, which is, let's say we got 128 by 128 blocks. So that's doing 128 by 128 additions of those matrix elements. So when I add those two matrices together, and similarly, when I'm doing this multiply, this is a matrix multiply now for those little blocks. So that's 2b cubed, where b is going to be the block size. So little b is the block size. And so we've got b squared operations in that addition and b cubed operation in that multiply. And so the picture looks almost the same, except now what I have to fit in my memory is not a row of A and a column of B, but 3 blocks, a block of A, a block of B, and a block of C. And I'm going to assume that those 3 things fit in memory, my fast memory that is. And now I can redo the memory analysis to see what my memory traffic looks like in this case. So I'll just point out that before I do that, let me just see, I think I might have reordered this slide. Okay, so let's look at our performance of blocked matrix multiply. So remember, M is the amount of memory traffic. So in order to calculate this, if the memory traffic in this case is going to be, big N is the number of blocks that we have, little b is B is the block size. And so we're going to have capital N of those blocks, each of size little n squared. Sorry, we're doing little n squared of those. And so we're reading those blocks n cubed times, but each of the blocks has size b squared. And so it's n cubed. Capital N cubed is the total, capital N is the number of blocks in each row and in each column. So let me just start over. Okay, so capital N right here is the total number of blocks in each row and each column. And then we're going to do n cubed of those reads once again, as we did before of the B matrix, except this time what we're reading is something of size B squared, so a little b by b block. And that capital N now is the number of blocks in the row, not the total number of elements. So we can convert that into the total number of elements, the little n squared that we started with. That's the original matrix dimension. But now we have, instead of having n cubed, little n cubed, we've got capital N times n squared. And similarly, we can read blocks of A and read blocks of C in blocks and get somewhat better formula, at least for A. And we're reading the, and C is kind of the same. We're just reading each element once. So, so this gives us we are going to now read through each one of these elements of A. We have to those in blocks, and we're going to repeat some of those as we go through the matrix multiply. But now my computational intensity here is not quite n, but it's going to be about b. So for a large enough value of n, so it's going to be little n that is divided by capital N, or b the block size. So this is going to give us a much better theoretical performance. And if we choose B carefully, it'll also give us much better actual performance. And we can do this kind of blocking both for any level of the cache. We can also do it for registers, although once we get to registers, we'll also look at a number of different types of register operations. Okay, so the question is, can I distinguish between slow and fast memory again? So slow memory is DRAM and fast memory is cache. That's the best way to think about it. Although I can also think about it as slow memory is cache and fast memory is registers. But for the purposes of right now and for homework 2, which you'll be looking at, you're really going to be blocking for the cache. So just think of it as that DRAM and the cache. And then the second question that came up is the implementations in practice try to place matrices in memory locations such that they don't conflict in cache and that has low associativity. And yes, and you're going to look at that in homework 2 also. You're going to look at how you may worry about at least, if not exactly where you place the 3 blocks, normally you'll probably have enough associativity that you don't need to worry so much about A, B, and C interfering with each other, but you do need to worry about the columns themselves or the rows themselves interfering with each other. You won't have enough associativity to store, say, B columns in those if the relative location of those in memory are not very well chosen. So you will look at that. Okay, so let me just go back and show a couple of performance numbers. This is from a group at ETH that did some blocking implementations of both, and there's a little lingo on here I should have written out. So DGEM is dense matrix multiply, and DGEM-V is matrix vector multiply. So this is the running time. So the y-axis here is time. And what you can see from this, for a given problem size, it takes a lot more time to multiply two matrices of that size than it does to multiply that matrix times a vector. Not surprising, this one's an order n cubed operation, this is an order n squared operation. So in terms of running time, you have to be very careful whether you're talking about running time or performance, or the floating point rate. So this time the y-axis is time, and on this slide, the y-axis is floating point operations per cycle, which you can think of as another way of looking at the megaflops per second, but this time it's per cycle, and given there's a constant clock rate on, well, not on all processors today, but let's assume the flop rate is constant. So we will end up, this is really another way of writing down a flops per cycle. And in this case, DGEM-V looks much better than DGEM, right? So up is good because you want to get more floating point operations done per cycle, and so it looks like DGEM is much better than DGEM-V, and it is because because this one is running at the speed, the blue line DGEM, the matrix multiply, is running at the speed of the processor, of the arithmetic units on the processor, whereas the green line is running, roughly speaking, at the speed of the memory bandwidth from slow to fast memory or from DRAM into cache. So higher computational intensity is better, given a fixed amount of work, right? So we've got a fixed amount of work we're doing in DGEM. So in DGEM, within this line, higher computational intensity is better. And generally, it's not necessarily better in the sense that DGEM just does less work. And so it turns out to be faster, but it's a different problem. You're solving a different problem. So for a given problem, higher computational intensity is better. Okay, now you're going to be looking at tiling matrix multiply, and we won't go look at this graph in detail, except it's from a fairly recent paper looking at how you pick the tile size for your matrix multiply. And this is some normalized metrics, because this was looking, I think, at different, it was looking at a number of different things. It's not really just looking at running time. So the blue, this sort of turquoisey line is running time. And so for each one of the blocks, and then the other things are cache miscounts, and the for the L1 and the L2, and there's the dark blue is the overall execution time. So you can see that for as you vary the tile size, it improves and then it goes up, and we're going to ask you to think about that in homework 2. But you can see a lot of crazy things are happening in terms of cache misses and so on in the middle here at various points, probably because of something interesting going on in the cache. Okay, so this just says that in theory, we have this nice blocked algorithm. We can prove that it's going to give us much better computational intensity. In practice, we do have to worry about exactly how to make these things fit into cache. So just to wrap up, for today's lecture. So there's a lot of details of machines that are architectures and microarchitectures that are going to be important for performance. We really were just looking at one of them today, which is this issue of the memory system, and really just thinking about it as a single memory hierarchy. That is the data off chip in the DRAM, and then the computation that's happening on the chip. And of course, we know that machines are much more complicated than that. But in practice, it does take hundreds of cycles to get to the main memory, and that the caches, although they're much faster, also are going to have to be smaller. And locality is going to be at least as important and often more important than computation. You know, we'll worry about both spatial and temporal locality. So mostly what we were optimizing for today was temporal locality, that is reuse, so that we could improve our computational intensity. When you start worrying about some of the issues of where the cache lines, what's actually in a cache line, we'll be looking at spatial locality as well. And then the question that we showed today, and for a specific example of matrix multiply, is that you can rearrange the code and the data to improve your locality. And the goal here is going to be minimizing data movement or minimizing computation. And I think with that, let me just see, I think it's 10 o'clock. Let me see if any more quick questions. Right, great. Well, homework 2 should be online within the next day, so please look for that soon, and we will see you here on Wednesday. And hopefully, and your homeworks are due tonight, so hopefully all of them will be turned in before 9 p.m. tonight. Don't use a slip date for homework 1, please. It's just not worth it, and I think it's better to get your homeworks in, but there are slip days, and you can read all about them in that overview. Okay, thanks a lot. Bye.